Welcome students. I would like to start this lecture about the industrial robotics by going in through some topics related to robot anatomy. Then we will move into the robot control systems, discussion about end effectors. Then we will review some of the most common industrial robot applications, and then a little bit intro to robot programming. So to start, we might define the robot like a general purpose programmable machine that has some certain characteristics of the bio-inspired organisms, like we have our arms. And then we will discuss how can we integrate the industrial robots into some work environments that are not necessarily safe for humans. So it might be something underwater, it might be something in a combustional, some kind of environment that it's not really safe for humans, or some high temperatures, or a lot of paint circulating through air. And also the reason we like to use industrial robots is that they do very well in the repetitive form, so they can do tremendously long cycles, and they can work 24/7 basically. And we do have to perform maintenance, but they can work longer shifts than humans. They can work very accurately, and they can perform the same tasks in given tolerances repeatedly. So we can make sure that they will be consistent and accurate. They can also do some tasks that are very heavy for humans. So we use them a lot in moving pallets and moving very heavy goods in the precise locations, and lifting so many different boxes at the same time. They can also work, like I already mentioned, 24/7, which means they can work in 3 shifts per day if needed. And the reason we use them is because they can run multiple programs, and they can be flexible and adaptable anytime we change the production settings and our industrial processes. So sometimes we might even develop these programs when robots are offline, so it doesn't have to necessarily stop production. And we can also interface them to another computing systems and make sure they're connected with other things that we're using in our manufacturing system. So if we take a look at this robot, we will also see differences in between what are the different parts. So if you take a look at here, you might find the base, which is always however robot is attached to the ground. And this robotic arm that is shown in this picture does not necessarily has to stand on the ground like this given robot is standing. It can also be attached to the ceiling, to the wall. So the base can be positioned on many different places, not necessarily just on the ground. But most commonly we will think about robots, something with a base which is attached to the ground, and then we have all these different things coming out of the base. So if you take a look at the picture, we will see we have base, then we have link 0, link 1, link 2, link 3, which is going to the end of the arm. And we can also have joint 1, joint 2, joint 3, and you might see where these links are connected. And if you see these hoses, this means that this robot has electro-hydraulic actuator, and there's this small bladder there, which is actually providing some hydraulic power to it. So if we review the text now, so joints provide relative motion. So relative motion in joints, we move joints, we rotate them. That's how we provide the motion. Think about them as our wrists and all these different joints we have in our body. So the links are these rigid members between joints. So it's like our bones in our systems. We have different bones that are in between our different parts that are moving the same way the robot does. So there are 2 various joint types. One is linear and one is rotary. The one you see in this picture, they're all rotary, But if you remember when we were looking the Mitsubishi robots, they can have, for example, end effector that opens up like this linearly. So we might say that they do have different kinds of parts. Some are linear, some are rotary. And each one of these joints provide a degree of freedom. When we say degree of freedom, is the way we can move, one way that we can move. So for example, if you take a look at my movement, this is 1 degree of freedom. This is maximum I can go. This would be minimum. So this, I have an angle that starts here and starts there if I'm only looking at that 1 degree of freedom I have in my hand. So most robots possess 5 or 6 degrees of freedom. That's very typical for industrial robots. And we might say that the robot manipulator has 2 main sections. The first one is body and arm. So we serve that for stabling it, positioning it, connecting it to the controller, connecting it to the power source, making sure it's safe, it's attached to some kind of structure. And then we have a wrist assembly, or that many times we call end effector, and whatever we put on top of that. And we use that for orientation of objects. So imagine I use my arm to reach my coffee, but then for the coffee operation, I need to have my hand. And I'm going to hold it like this. But imagine if I would be welding, I might have here a welding tool that I would use, and with that tool, I would be welding. So depending on the process that we're going to do, we will have different kinds of wrist assembly. So we use the following joint notation scheme to identify how are we going to designate the joint types used to construct the robot manipulator. We can use LORTV, and we can separate the body and arm assembly from wrist assembly using a column. So we can say what kind of things we might have in it. So one example is TLR, TR. So let's review some of them. So the first one that we're reviewing here, it's called polar coordinate body and arm assembly. And if you take a look at here, the base is rotational. So we do have that axis that moves around like this. And then we have here another rotation on top of it. And then we have, so it's like basically moving along two axes with rotation, and the third axis will be the linear one. So that's why we say T, notion of T joint is our vertical axis, a sliding arm will be our L joint, and the horizontal axis will be our R joint. So we have a sliding arm, which is basically some kind of linear movement, which is actuated relative to the body, which can rotate about both vertical axis, T joint, which is rotation, and horizontal axis, R joint. So this robot will give you example of the TRL configuration. So the second one will be the cylindrical body and arm assembly. And in this one, you will have a vertical column, which have a Z rotation. And then we will have an arm and assembly that can move up and down. So basically, we will have two other that are going up and down in some kind of Cartesian coordinate system. And this arm can be moved in or out relative to the column. So rotation, and the other thing is to basically horizontal axes, X and Y, for example, and the Z is rotation. The following one is a Cartesian coordinate body and arm assembly. There we use notation LOO. It consists of 3 sliding joints, and 2 of which are orthogonal. And other names include rectilinear robot or XYZ. This is very typical. We call it Cartesian because we understand easily how this moves. We go X, Y, and Z. Um, in So we have these a lot in industry, in material handling. You see example right there. So if you would investigate where are applications of these, you might find maybe some kind of cutters that are using lasers to cut the pieces of something, or you might find some kind of water jet machines, or you might find engravers or something like that, something that has horizontal operation. Then we have a joint arm robot, which has notation TRR. So look, the T is for the base, which is rotating, and then we have two other rotational components. So if you pay attention to these three axes, all of them are rotational. So we have 3 degrees of freedom here in TRR, and they're all rotary. So very typical robot that I would like you to review is SCARA. It has notation VRO. It stands for Selectively Compliant Assembly Robot Arm, and it's very typical in many of the industrial packaging applications. So this one is similar to joint arm robot, except that vertical axes are used for shoulder and elbow joint to be compliant in horizontal direction for vertical insertion tasks. So can you imagine if we would work like this? You know, the arms are in the same level and we're trying not to move on the other one. So something like that. That would be mostly our SCARA robot. And there are different wrist configurations you can have. Basically, this assembly is attached to the end of the arm. So look, the darker blue is where the robot arm ends, and then we have the whole wrist there. So depending what do we want to achieve, and most commonly, we will have the end effector, and the end effector will be sub-assembly that you can attach something else. So if it will be a tooling, maybe welding gun or spraying gun or something like that, we might put a camera there if we want to spy with our robot, do something. We might have machining tool. We might have anything that we need to achieve some kind of industrial operation, some kind of processing or material handling or inspection. We might add that to our wrist configuration. So these have 2 or 3 degrees of freedom. One might be roll, pitch, and yaw. And notation for this is RRT. So if you take a look at the picture, so you see the one which is in the same axis to attachment to the robot arm, it's called roll. And then we have 2 others that are pitch and yaw. And if you're using any of these accelerometers that are measuring you know, how many steps you did per day or something like this, they're basically capturing your pitch, roll, and yaw. And based on that information, they will think that you are exercising vigorously or you are barely moving or something like that. You might see different sensors that can also measure these things that can be wearable electronics. So here, if you would like to review the sketch for the following manipulator configurations, you can see here T is always for the base. So you see T is the base. And anywhere we have rotations later, we will put R's. Anywhere where we put some kind of translation in between, we might put T over there. So in terms of how we drive our industrial robots, we might have different drive systems. They might be electric, hydraulic, pneumatics. If we are lifting very, very, very heavy stuff, hydraulic is the way to go. If we want to do something very fast, very abrupt, and many, many, many times, and it's not really high forces we want to achieve, pneumatic is the way to go. But if we want to do something on precise location and we're changing location throughout the time, maybe electrical will be the preferred way to go. So you will see hydraulic might be slow, pneumatic fast, electric in between. but in terms of forces, in terms of the environment, we have to have all these things that we have to worry about when we want to decide which one of these we would go. So if you look at the electric, the first one you see there, it's some kind of servo. It uses electric motors to actuate individual joints. So the one we have in Kaufman Hall lab, robotics lab, they're all actuated by electronics, and they all have electrical motors, and we have to have different kinds of power. For industrial arm needs a specific stronger power, then a controller needs another kind of power, and then we need power for computer as well. And in terms of hydraulics, we need to use the example which I show you in the first picture here. That one had hydraulics. You see, I see a bladder. I see, anytime you see some kind of pressure gauges or something, you know for sure that's measuring some kind of pressure. So it's telling you that, and anytime you see hoses or something like that, you know that that device might have some kind of hydraulics inside. So we love to use them because they have really high power, the very good lift capacity. They're working slower, but we do need many things to work slow sometimes, especially when we're lifting things. And we can, the reason we like hydraulics is anytime you lift something, you have to hold it. And if you do it with hydraulic power, it's easier to maintain the same amount of force that you're holding something. Then in electrical, we need to put different kinds of signals, and sometimes the electrical motors doesn't have enough torque to hold something still for a longer time, especially if it's heavy. And in terms of pneumatics, we use it for smaller robots, simple material transfer applications. So anytime you see these pick-and-place robots, they have vacuum suction cups on top of them, that's most likely pneumatic robot because it works like, and many times you will hear a noise of pneumatics in the system. So, or if you see blue lines, that's a good tip with dealing with pneumatics. In terms of the control systems, make sure you understand that anytime you want to integrate industrial robot in manufacturing system, that you have to have accommodation for the control system that it's needed. So many times you buy, for example, here in the picture you have ABB robot, it will have its own ABB control box. If you buy KUKA robot, it will have KUKA control box. If you buy Adept robot, it will have their own systems. And many times you have to understand how to maintain safety of these control boxes. You don't want to have somebody jeopardizing the cybersecurity of your system and, you know, making sure this box is open, easy to access, and some of these systems are disconnected. So in terms of robot control systems, we have limited sequence control. We use that when we have pick and place operations, when you need to use mechanical stops to set positions. Then we have a playback with point-to-point control. Then we have to record a certain work cycle, a sequence of points, and then place back that sequence during the program execution. Example is when you have to do welding. I do spot welding, and I have to do weld, 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 weld. Or I do painting, then I have trajectory I'm following. And then playback with continuous path control. This requires a greater memory capacity or an interpolation capability to execute path in addition to point. For example, when we want to do CNC of a turbine blade or something very crazy shape, we might have a robot holding the milling thing, and then it goes slowly and start making these turbine blades slowly. But we care about every single point. So in spot welding, it's point, weld, point, weld, point, weld. But when you have continuous path control, we care about every single point throughout the way. And also, we have robots that have intelligent control, and they might have some kind of behaviors that make them seem intelligent. For example, response to sensory inputs. So when you have cobots, and if they will detect something in their environment, they might slow down, they might reduce the fork torque, because they would think maybe human is present and they don't want to hurt you. And they will make decisions based on that. And they might see they can communicate with humans, maybe put some kind of warning systems or different things like that. So in terms of robot control system, you will always have a cell supervisor, and under the cell supervisor, you might have controller and program, and then you have to dedicate the same kind of program. Uh, I mean, it has to be configured that you are achieving what you were planning to achieve, either if it's pick and place, or it's a different points, or continuous loop control. And you have to make sure that, for example, if we have 6 degrees of freedom, we will have these 6 joints that we will have to control in every single time. And my controller from the robot have to talk to every single device, every single of these 6 different if it's electrical, hydraulic, or pneumatics, I have to control each one of these 6 different actuators. And remember, they can be electric, they can be pneumatic, they can be hydraulic. So I'm maintaining the control of all these different subsystems through there. And usually I have a bunch of sensors there in the robot that can help me see if I'm performing my task the way I was supposed to. So the end effectors, these are the things that are attached to the robot arm, and they are very different in depending what we want to do. Some of them are grippers, the one that can lift something and we can hold it, or they can be tools. We're welding, we're cutting, we're doing something with them. So they vary greatly based on the task that it's giving. So here in this example, you might see some of them resemble human hands, and you see they have a bunch of these different dental flosses trying to move the one on the top. Or you might see how some of these, so the one black left up basically has different servos, and in this case it has 2 servos, and the servos are used to open and close linearly this gripper. The one that looks like chrome, it's used for spot welding, and that one delivers high amperage to the 2 metallic parts that we want to attach together with a spot weld. And you will see here there are different designs. The other one looks also like some kind of welding cutting tool, and so you can see that they can look pretty much different depending on their application. The robotic working envelope. So imagine you are sitting on the chair and try to span your arms to the front. This is my working envelope, end of my fingertips. And if I span all my arms and see where it is, pretty much similar to this robot. That's my working envelope. And I cannot really say that at the end of my fingertips I can really work. It's more somewhere where I can do something with my hands. So maybe my workable envelope, it's less than if I do the maximum span. So the working envelope, it's a little bit different when you think about these different things. Maximum envelope, whatever I can hit. Restricted envelope, it's the one I really work in, and operating is where I perform the best. And if I do the program, that's the one that I will actually that I can work. And you can see in the 2D world on the 3 images on the top, and you can see on the lower images that it's actually a 3-dimensional thing, and many of it is related to how that robot is designed and how it works. And it doesn't really move like from spot to spot. When you use these robotic arms, our movements are a little bit different. We're using different kinds of space. So that's why the shape is not so straightforward when we look at understanding. So if we review some of the industrial robot applications, we have different things that we have. So they can be material transfer, pick and place, palletizing. They can be machine loading and unloading. Some of them can be processing operation. We can do welding, spraying, cutting, grinding, any kind of machining, and very, we can also use robots to do maybe 3D printing, to hold spray nozzles, and we are melting some kind of metal with them. We can also use them for assembly and inspection. We can put different tools on the robots, and we can send them somewhere where we cannot go. Nuclear plant, we can send them there to do data collection, analysis. Underwater, we can send them way deeper than we can ever dive. We can send them to space. We can send them in dangerous environments that we would not be able to go to. So if we review where the robots live in the world, these are the top 10 countries by robot density. And imagine which is number one: Japan. Then the second one is Singapore. Then we have South Korea. We have Germany, Sweden, Italy, Finland, Belgium, US, Spain, and in regional averages, you can see how many we have in different places. And this is example of one robotic arc welding cell. So you see, we would put the robot in between. We're connecting the robot to the controller, to the power unit, and then you might see what kind of different things are attached to the robot. So there's a different support, and the weld wire delivery system, it's spanning over the robot, and you will see how the welding gun works. And there are different fixtures that are made, and the robot is programmed to work with these specific welding fixtures. And here you can see a flux cord arc welding operation, and you might see there human operator at the end. Many times we will put all of it in cage, or we will have some kind of protective equipment around it if it's welding, because most of the welding operations are not very safe for human eye. So in terms of robotic programming here, I will just mention it, and then later we will review what are the different software for different companies. So depending on what robot you buy, is it KUKA, is it Adept, whatever you have, you will see how you define these different programs. So we will say it's a kind of work cycle, and we might use, for example, we might have a cell that's already built, and we might move robot and save different locations. So if I mention spot welding, we say, okay, this is location, save it, location, save it, location, save it, location, save it. And then we will know these 3D locations. Or if we have a virtual cell, we have everything drawn on the computer, and we can move the robot to different places and figure out how to approach different points that we want during the motion cycle. So, and also there are different robot programming languages. There's some textual programming languages to enter commands directly into robot controller, but also we use a lot, especially now in 21st century, we use a lot simulation and offline programming, where we can develop program and then we can upload the program to the robot and make it run. So basically, it's very similar when you would have a 3D printer and you have your STL file, you convert it to additive manufacturing file, it's a G code. We can also make some kind of G code for all of these different robots, or see how we will move these different joints. So remember, when we develop a robot controller, we have to understand that all 6 joints will need specific information, which is different for each one of them at each given moment. So the program is usually prepared at a remote computer terminal and downloaded to the robot controller for execution. So that's what we usually do. So here an example, you might see the lead-through programming. Basically, it's very common for point-to-point robot. You can use teach pendant. And then if you were welding, you say save this location, save that location, go there, come back here, and then we save these different small points. We can do manual lead-through, and it's very convenient for continuous path control robots, and human programmer is required there to program the robot how to move. And here, this is example of one human interface. You might see LED display for speed. You might see the speed control. You might see the record location, the motion control. You see we have record, joint, world, tool, mode. and we might have gripper open close, and we can toggle switches for different joint control. So this specific robot has 6. And when we say XYZ, these are probably XYZ, RX, rotation around X, rotation around Y, rotation around Z. So the main advantage why you would do lead-through programming is it's easier for shop personnel. You don't need to require people with higher degrees. It's a logical way to teach a robot. You don't need to understand computer programming. You will just pre-save locations that you need. Disadvantages, you have to stop everything and you have to be only making robot available for this. So you will have some kind of downtime, and you have limited programming logic capability, and it's not compatible with supervisory control because we're making this kind of program and then it's not working remotely. So in terms of robot programming, there are different various textual programming languages. Many of them can also have in-chase sensor capabilities, and depending on what kind of sensor you integrated, they can also have the output capabilities to control external equipment and enable the Internet of Things approach. They can also provide you with the program logic, and they can also have computations and data processing, and they can provide the communication with supervisory computers by you knowing the exact IP address and different information related to the specific thing that you want to access. So in terms of coordinate systems, we have two different. We have the world coordinate system, which is the one that we use usually attached to the base. And then you will see the end of the arm moves are parallel to the world coordinate system axis. Or we have the tool coordinate system, which moves are relative to axis systems defined by the tool orientation. So you see it's different how we define the coordinate system for calculations. Are we thinking about the base, or are we thinking about the end where we're trying to go with our robot? This is one example of the motion command. So we can say move P1. Here P1 using during lead through a manipulator moves P1, D move, we have approach, depart, define path, move path, speed, and we can define what is the speed there. And when you define the path, for example, in this case, 1, 2, 3, we will say that path 1, 2, 3 has 3 points, point 1, point 2, point 3. And we say move path, go 1, 2, 3, it will go through these 3 points. And also there are different interlocked commands that we use for pausing some kind of periods in between operations. So we can say turn it on and wait for 20 seconds most likely. Then we do signal on. Then we can do some react, save stops. And we have a gripper command, open, close, open this much, open this, differences in terms of how much you open. And this is example of one of the offline programming software. You can see you have a robot there, and also you can go to some of these manufacturers' website, download some of these robots. You can open Inventor. You can insert in assembly one of these robots, and you can see how it looks in the world and what kind of space it takes. So here are a couple of examples that I want to show you. So the first one is a robot performs a loading and unloading operation for a machine tool as follows. Robot pick up part from conveyor and loads into the machine. We need 5.5 seconds to do that. Pick and load to the machine. Then the whole machining cycle might be 33 seconds. And then the robot goes and get the part from machine and put it back to the conveyor. Not a conveyor, that's 4.8 seconds. And then the robot moves back to pickup position, 1.7 seconds. So how much time do we need for all of this? So if we're only machining one part, we need 5.5 plus 33 plus 4.8 plus 1.7. So if we would do 30 work parts, the cutting tool and the machine are changed, which takes 3 minutes, and the uptime efficiency of the robot it's 97, and the uptime efficiency of the machine tool is 98, which rarely overlap. So here the question is, what will be the hourly production rate? So here, if we want to define how many seconds per cycle, we put all of these times, 5.5, 33, 4.8, 1.7. So we need 45 seconds per cycle. If we need to change time, we need to change, we will split that time, so we need 3 minutes, and we have 30 pieces. We would say average is 6 seconds per piece. We have to put that into account. And then the robot uptime is 0.97, which means that 3% of our time will be lost. And then the machine uptime is 98%, so 2% of that time will be lost. So when we calculate the total time, we will say, okay, we put these seconds per cycle that we're actually working. We're putting this 6 seconds per cycle that we're actually changing the tool, and that together will be 51 seconds, or 0.85 minutes per one piece. And then if we consider that will be per hour 70.59 pieces per hour that we can make. And then if we add uptime efficiencies, we will see that it's less than that. We can maybe count that we'll make probably 67 pieces per hour. So this is how you would calculate how many pieces per hour you can make given your different times that you need in operation, different times related to the tool change time and uptime and different efficiencies that you have in your process.